Welcome to this fifth lecture of this lecture series. Now, in the last lecture, we have seen how to design constant k filter section using image parameter method. Today, we will point out two major drawback of this design. If we look at the graphs, yesterday we have drawn these graphs, that the characteristic impedance of the section for, if we take a T section, the characteristic impedance falls from a constant value k at 0 frequency to 0 at cutoff frequency. So, characteristic impedance is changing. So, it is a problem for matching the filter section impedance matching. Similarly, this is the graph for the pi section characteristic impedance, and you see here also from constant k it goes to very high value. So, it is very difficult to match this. So, if we cannot match, then there will be reflections and some power will be lost. So, even if we are using a lossless filter, but due to impedance mismatch between source and load side, there will be some problem and that needs to be rectified. Also, if we look at the attenuation constant graph, we see that in the passband, from that means frequency from 0 to fc, the filter is this for low pass filter, it is that there is no attenuation, but once it crosses the pass band in the stop band, there is attenuation, that is also desirable. But you see that near this cutoff frequency, near this zone, the attenuation value is not much. So, if I have another channel very near to this cutoff frequency or another radio signal, then the attenuation will not be much. Once it is separated by a reasonable distance, then it goes to high value, and it is also desirable that when omega is very high, the attenuation is infinite. That means, this portion that is but this portion in some applications may not be acceptable, because we want that in stop band there should be a good amount of attenuation, but near the stop band edge for this constant k section, the attenuation is not much. That is why this is also another problem. So, these two problems motivated people to design a better filter section. That design is called m-derived filter section. So, what is an m-derived filter? Almost same as our constant k filter. I start with pi, I start with T section. So, this is the same as T section, it is a symmetrical section, reciprocal element, lossless element, all these are reactances. So, I call now the new series impedance as Z1 dash by 2. So, I am using a dash or primed quantities to represent this, and this I call Z2 dashed. So, this is m derived. Now, what was our constant k? That was Z1 by 2, Z1 by 2, Z2. This was constant k. Today, we are saying it is Z1 dashed. Now, this is m derived. So, how this m term comes? Actually, we let Z1 dashed is equal to m Z1. That means, we just m is a parameter, we multiply Z1 dash with this parameter, and then we want to keep the characteristic impedance for same with constant k. So, what was the characteristic impedance of constant k? If I call that Z naught, this time I am using a subscript k to remind you that this is constant k, that was root over Z1 square plus 4 Z1 Z2 by 2, and the new m-derived filter characteristic impedance will be Z1 dash square plus 4 Z1 dash Z2 dash by 2. Now, we do not want to disturb this characteristic impedance. So, we equate these two. So, we say that these two are equal. Once we say that, then we can find out Z2 from here, because Z1 dash we have expressed in terms of m Z1. So, by solving I get Z2 dash is equal to Z2 by m plus 1 minus m square by 4 m Z1. So, if you remember that Z1 and Z2, they are the impedances of the series and shunt arm of the constant k section, and if you remember that always to have filter action, they should be of opposite nature. That means, if one is chosen as L, another is C, and depending on whether I choose L in the series arm or C in the shunt arm, I get a low pass or high pass action, etc. So, now you see that this equation says that Z2 dash, it will be now two elements. One is a scaled version of Z2 and in series with a scaled version of Z1. Okay. So, the new m-derived section I can draw as so, this will be Z2 by m, and this will be 1 minus m square by 4 m Z1. So, it is a series circuit in the shunt arm. So, this is the new design. So, we have seen the propagation characteristic impedance. Now, we have already known that filter has two fundamental characteristics. One is characteristic impedance, another is the propagation constant. Let us see what happens to the propagation constant in this case. So, this propagation constant, if you remember that yesterday we have derived this tan hyperbolic gamma is equal to root over Z1 square by 4 Z1 Z2 by Z1 plus 2 Z2. So, from here we will have to find out e to the power gamma. It is easy to do, because this tan hyperbolic gamma is equal to sin hyperbolic gamma by cos hyperbolic gamma, and you know sin hyperbolic gamma is e to the power gamma minus e to the power gamma by 2, e to the power minus gamma by 2, and cos hyperbolic gamma is e to the power gamma plus e to the power minus gamma divided by 2. So, if you do that and then some component or dividend algebraic manipulation, you get the value of e to the power gamma. So, e to the power gamma will turn out to be simple mathematics 1 plus Z1 by 2 Z2 plus root over Z1 by Z2 1 plus Z1 by 4 Z2. This is the expression always we get. Now, we are looking for m-derived section. So, let me put primed quantities here, e to the power Z1 dashed. Okay. So, this is the expression for e to the power gamma. Now, from this, since we know the values of Z1 and Z2 dash, we can find out for a particular type, low pass or high pass, that what happens to gamma, and once we have this expression for gamma, we can enforce the stop band and pass band specifications, and from that we can find out what is the stop band, pass band, etc. So, let us do that for m-derived low pass filter. So, we need to choose Z1 in constant k, we choose Z1 is equal to j omega L, Z2 is 1 by j omega C, this is constant k. So, Z1 dashed for m-derived section we will choose as j omega L m, and Z2 dashed as 1 by j omega C m plus 1 minus m square by 4 m j omega L. Okay. So, now I can draw the in the component level, this will look like this, that I have so this will be m L by 2, this will also be m L by 2, this will be m into C, and this will be 1 minus m square by 4 m into L. Okay. So, this is a m-derived section. So, find out, as I said, what is the propagation factor. Now, if we look at the propagation factor expression, there is a this factor, important factor Z1 dash by 4 Z2 dash. If I know that, I can find out a lot, because this factor is all this you see are Z1 dash by Z2 dash, Z1 dash by 2 Z2 dash. So, if I can find this, then I can have various, I can easily find out the propagation factor. So, let me find out what is this value Z1 dashed by 4 Z2 dashed. You will be able to do this, because Z1 dashed expression is given, Z2 dashed expression is given. If you do this, it turns out to be like this. Good. So, now once we have this term, we can enforce passband. We know that always for this in image parameter method, this passband is like this. Passband is when minus 1 less than Z1 dash by 4 Z2 dash less than 0. So, this if we manipulate, we get that four minus 1 minus m square omega square L C by m square L C greater than omega square greater than 0. So, as we do that, you can put this part, that means the passband is extending from 0 omega, omega is equal to 0 to omega is equal to this value we can say as omega c, and then we can solve for that. and that will turn out to be omega c is 2 by root over L c, or f c cutoff frequency is 1 by pi root over L c. So, you see that for m derived section also the cutoff frequency is same. So, the pass band extends from 0 to f c, that means 0 to f c. So, alpha will be something like this. So, there is no change in the low pass filter structure. So, then what is the stop band? Stop band is, as before you know, that again since I have this quantity. So, I can enforce that if this quantity is either it is greater than 0 or it is less than minus 1, I have pass bands. So, from that I can say that the stop band according to our yesterday's nomenclature, stop band 1 will come out to be when f is less than 0, but we cannot have less than 0. So, it is not possible. So, we did not bother about this stop band, and the stop band 2, that will be when f is greater than f c, obvious, that is why I have drawn like this, knowing this that f c will be like this. Now, then what we have gained in m derived section? The cutoff frequency is same, etc. We have enforced the characteristic impedance to be same as constant k section. So, then what we have gained? To see that, look at z 1 dashed by 4 z 2 dashed expression carefully. I rewrite that again here, that z 1 dashed by 4 z 2 dashed, this is omega square m square L c by 4 minus omega square 1 minus m square L c. Now, look at the denominator. There is a chance that denominator may go to 0, and if that goes to 0, this whole thing will become infinity. So, that is a crucial point. It was not present in constant k. Let us solve this. Let us say that at that frequency when this happens, let us call that omega infinity, because this will go to infinity there. So, what is omega infinity? If we solve, we get that omega infinity is equal to 2 by root over 1 minus m square L c. So, what is my omega c for constant k? 2 by root over L c. Omega infinity is 2 by 1 minus m square L c. Okay. You see, this is omega c. So, if I enforce that m is a parameter that I will choose, I will keep it within 0 to 1. It is in my hand, designer's hand. If I keep it like this, then omega infinity is greater than omega c, or f infinity is greater than omega c. That means, f infinity is in the stop band 2. So, in this band there is a this thing, but what happens to the alpha there? Let us see the e to the power gamma expression, that will indicate what happens there. So, you see that e to the power gamma expression is this. Now, here this term is going to infinity. Now, obviously, at that point this term will be also high. So, you see this is infinity, then this is also infinity. So, the whole thing is infinity. So, can I say that at that point gamma at omega is equal to omega infinity, my gamma goes to infinity. So, gamma is very high. Now, what is gamma? Gamma is alpha plus j beta. We have proved that we are at stop band 2. So, at stop band 2, what is the, we know that beta is a constant, it is equal to 2n minus 1 pi. So, let us say pi. So, beta is constant, but alpha plus j beta, that is very high. So, that means we have alpha also is going to infinity there. So, that was the thing we were looking for when I said that the problem of this constant k section is near Fc I do not have sufficient alpha, but I see here that I can place a pole very near to Fc, because that I can control by choosing this parameter m, because where is Fc with where is f infinity with respect to Fc, that is in my hand, because I can play with this m value and I can put anywhere, and then I can modify that. Okay, the attenuation constant graph alpha, this is Fc, suppose I put, so obviously here that it will come like this, but then I have a choice that if I put suppose f infinity here, then I can force the curve to go like this asymptotically. Sorry. So, I can give a very high attenuation just when I enter the stop band, which was desirable, because many applications says that do not disturb your neighboring channel. So, there I can put sufficiently high attenuation. So, how we are able to do this f infinity? You look at this structure of m-derived section. Basically, I have a series circuit. This series circuit, if it goes to resonance, this series circuit if it goes to resonance, that gives that high attenuation. So, it becomes a resonance circuit. Let us check whether we are physically it is correct or not. So, we know that if we have a series circuit like this, what will be the resonant frequency? F resonant for that will be Fr is equal to what? That 1 by 2 pi root over mc into 1 minus m square by 4 m into L. This m and m goes, and so I get 1 by 2 pi root over 1 minus m square L c, which is nothing but my f omega. F omega is this 1 by pi this. So, that shows me that 1 by pi, that shows me that yes, physically that is the case, since I have this series resonant circuit, I can make it resonate at f infinity, and by that I can put a very high attenuation in the stop band. But the price I pay for that is unfortunately this thing that after f infinity the curve is like this. So, alpha again falls. So, I also want that at very high values or all further values the attenuation should be high, but you see attenuation is falling due to this m-derived section. So, I can solve one problem, but then in constant k this was not a problem. In constant k it was going exponentially. So, in constant k, where is the constant? Yes, in constant k it was rising. So, at very high frequencies it was high, but due to my playing I could solve the problem here, but I have created another problem here. So, this is a problem that, so let me draw once again the attenuation constant of m-derived section, that there will be f c, there will be f infinity. Now, I can put it such that it comes here, then it goes to very high value and then it falls like this. This is the m-derived section, alpha attenuation constant. So, what is the remedy? Remedy is we need to put in cascade with this a constant k filter section. Let us see what is a constant k filter that we have seen that time, that its thing is something like this. So, here you see this is a very sharp increase. So, I will not have any problem, these two if they in cascade when I put alpha will be almost like this, and here also it is a very sharp decrease. So, it will be dominated here also like this, but then here you see that this constant k section, this is constant k, this is m-derived. So, if I combine, then I get something which is called composite filter. So, I get a attenuation constant frequency response that, let me mark f c, let me mark f infinity, and it is this, then it goes almost like this, then it comes and then goes like this. So, this is called composite of m-derived in cascade with a constant k. So, there you see that I will have to be careful about this part, that this alpha should be acceptable for the application. That means, nearby neighbor or next to that channel there is a low attenuation, but if this is sufficiently high, this level for that application, I can go with it. I am rest assured that henceforward it will be higher and higher attenuation. So, this, but you see that I have started with two problems, that means, this alpha was not very high here. So, that at least with this composite design I have solved this problem, but this problem is still unfinished, because we have enforced m-derived section to be have same z naught variation with constant k. So, characteristic impedance problem I have not solved, m-derived section has not solved this problem, but what people do then to match the section, there are some extra matching section at the load end and the source end they put. So, that makes this whole filter thing a bit bulky and all. So, that is the problem with image parameter method, but something is done, and throughout this development for last 60-70 years, people have used that in telephony, in radio reception, etc. These filters were designed from this image parameter method, but as we saw that this problem can be solved if instead of all these problems, that means, we try to find out, okay, if we choose this, how it happens. If we can say that from a specification, I will specify what is my stop band attenuation, I will specify what is my stop band phase, pass band phase, I will specify what is my pass band attenuation, that should be 0. So, all this if I space, always 0 is not required, because in application I require that, okay, to a sufficiently low attenuation. So, I will specify that, and that if we can find out that what type of filter components, that means, what LC values, how they are interconnected, there if I can find that, that means, basically a synthesis type of thing, that I will specify some attenuation characteristic, and from that you find out which sections, which components can achieve that. So, that is called insertion loss based filter design. All high frequency filters, microwave filters are based on that. So, that will take up in the next lecture, but these up to this image parameter based filter design, that gave us insight about what happens in a filter, what is the characteristic impedance thing, how it is very important for matching the filter, and also how to specify passband, stop band of a filter from the propagation constant point of view. So, that is the basic foundation on which we will see how insertion loss based filter design can be attempted. Come to the next class.